we just saw that null spaces and column spaces are both vector spaces. What I'd like to do now is illustrate how the study of null spaces can also be accomplished via the study of column spaces. So I'm going to present two examples now. In this first example, we're going to start with a matrix A, and we're going to learn how to write the null space of A as the column space of a different matrix. So let's say we were trying to describe all vectors that lived in the null space of a matrix. Well, the defining equation of the null space is all vectors that we can multiply A by to produce the zero vector. So what we would do to describe the vectors in the null space is we would row reduce our matrix. So here I have a 3 by 5 matrix A, and I've row reduced this matrix. And note here I have 2 pivots and 3 non-pivot columns. Now, if I were trying to describe all vectors in the null space, what I would be doing is I would be describing all vectors V that satisfy the equation A times V equals the zero vector. Well, how could I better describe those vectors? I can look at this system of equations and write the dependent variables in terms of the free variables. Here, the dependent variables will be the first and third variables, and the free variables will be the second, fourth, and fifth variables. So I know that all vectors V in the null space have 5 variables, but the second, fourth, and fifth variables can be written independently as free variables, and then I can use the reduced row echelon form to write the dependent in terms of the free. So if we were studying the null space, the first equation here would be the first dependent minus 2 times the first free, minus 7 times the second free, plus 5 times the third free equals 0. And by solving for the dependent in terms of the free, I get the first coordinate equals 2c1 minus 7c2 plus 5c3. The second dependent variable here can be solved for with the second equation. That equation would be v3 minus 3 times c2 minus 8 times c3 equals 0. And when we solve for v3 here, we get 3c2 plus 8c3. And so now I have the complete solution vector to AV equals the zero vector. And we can separate this out as a linear combination of 3 vectors. Here I'm organizing the coefficients of C1, C2, and C3 into 3 separate vectors. So this is something we've been doing for a few lessons now, but I want to emphasize that this has consequences on the level of theory. What we're doing is we're saying that every vector in the null space is really all linear combinations of these 3 vectors. So another way to say this is that the null space of our original A is the same thing as the span of the 3 vectors that popped out of this process. And since the span of a list of vectors is the same thing as the column space of the matrix obtained by inserting those vectors in the list into the columns of a matrix, this is the same thing as saying that the null space of our original A here is the same thing as the column space of the matrix obtained by taking the vectors that popped out of the process and putting them into the columns of a matrix. And here we're calling that new matrix B. So here we have an example of starting with a matrix A, studying its null space, and rewriting the null space of that matrix as the column space of a new matrix. So we just saw an example of converting a null space into a column space. Let's look at the reverse. Here we're going to convert the column space of a matrix into the null space of another matrix. So let's now describe all vectors V in the column space of a matrix. So here what we're looking at is a perfectly good 4 by 5 matrix A. And let's say we wanted to describe everything in the column space of this matrix. What we would do is we would augment with a vector v1, v2, v3, v4, and we would row reduce and make sure that we don't have a pivot in the augmented column. Well, here what we find is whether or not we have a pivot in the augmented column hinges on whether or not these 2 entries in the bottom right-hand corner of our reduced matrix equal 0 or not. So in order to make sure that we don't have a pivot, we need 7v1 plus v3 to equal 0, and we need negative 6v2 plus v4 to equal 0. So what we're saying is that every vector v in the column space of A for this example must satisfy the two equations 7v1 plus v3 equals 0 and negative 6v2 plus v4 equals 0. But if we look at these two equations, we realize this is the same thing as saying that this matrix times v equals the 0 vector, where the matrix we're extracting is the matrix of coefficients from this system of equations. The first equation is 7v1 plus v3 equals 0. So the coefficient matrix is 7, 0, 1, 0. And the second equation is negative 6v2 plus v4 equals 0. So the second row in our coefficient matrix is 0, negative 6, 0, 1. So now, all vectors in the column space of A must satisfy the equation this new matrix times that vector equals the 0 vector. Well, let's call this new matrix B, and what we're realizing is that the vectors in the column space of A must be in the null space of B, because the vectors in the column space of A satisfy the equation B times our vector equals the 0 vector. So what we've just done is we've just justified that the column space of the matrix we started with A equals the null space of the matrix we constructed here, B. So here we started with a matrix, A, and we rewrote the column space of this matrix as the null space of a new matrix called B. So this illustrates that the theory of column spaces and null spaces is unified under this concept of a vector space.